So we were discussing steady, compressible one-dimensional flow, and in the last section we studied normal shock wave. Now let us study what is known as Rayleigh flow. It is also known as flow with heat transfer. Now look at the control volume. One is upstream of the control volume and two is downstream of the control volume. The state of fluid is changing from at point 1 to at point 2, and this change is brought by heat transfer between the fluid and the surroundings. So Rayleigh flow is nothing but flow with heat transfer. Many compressible flow involve chemical reactions such as combustion, nuclear reactions, evaporation, condensation, etc. All these are example of Rayleigh flow. In combustion, fuel and air mixture burns and generates energy. Similarly, in nuclear reaction also, the nuclear fuel burns and generates heat energy. So in Rayleigh flow, what we do is that we model the generation or absorption of thermal energy as heat transfer through the duct wall at the same rate and disregarding any changes in the chemical composition. We neglect changes in chemical composition. We only consider heat transfer. And these are the governing equations which will govern Rayleigh flow. The first one, as you all know, is continuity equation. Rho 1 u1 is equal to rho 2 u2. The second equation is momentum equation. P1 plus rho 1 u1 square equals P2 plus rho 2 u2 square. Look at the third equation. This is energy equation. Since our flow involves heat transfer with the surroundings, we have to add Q in the energy equation. So our energy equation is H1 plus U1 square by 2 plus Q equals H2 plus U2 square by 2. The fourth equation is equation of state. The fifth equation is H equal to CPT, which is true for calorifically perfect gas. And our last equation is the second law of thermodynamics. Now all the properties at point 1 are known to us, and we have to find out properties at point 2, and we will assume that gamma and heat capacity Cp are constants. So how to find properties at point 2? So given the initial state 1, there will be an infinite number of possible downstream state 2. So to solve these equations, what we do is that we assume various values of T2. And calculate all other properties as well as the heat transfer Q for each assumed T2. From these governing equations. And for each initial condition, we can assume different values of T2, and we can plot TS diagram. Which will be a curve, and we will call that curve Rayleigh line. This is Rayleigh line or Rayleigh curve. This is a TS diagram, and we can make several observations from the plot. The first one is that for a given initial state, the fluid cannot exist at any downstream state outside the Rayleigh line on TS diagram. That means for a given initial state, there exists a unique Rayleigh line. If we change the initial condition, the Rayleigh line may change. And if we fix an initial state, then the fluid cannot exist at any downstream state outside the Rayleigh line. The second observation we can make that entropy increases with heat addition or heat gain. You can see that with heat addition, with heat addition, entropy S is increasing, and at mark number 1 and at mark number 1 point A, entropy S is maximum. Entropy is maximum. So point A is the point of maximum entropy. The upper arm of the Rayleigh line represents subsonic flow, and the lower arm of the Rayleigh line represents supersonic flow. The upper arm represents subsonic flow and the lower arm represents supersonic flow. And you can see that with heat addition, a process proceeds to the right side on the Rayleigh line. To the right side on the Rayleigh line. The third observation we can make that heat addition increases the Mach number of the subsonic flow. This is a subsonic arm, and if we add heat, you can see that its Mach number will increase, and if we keep on adding heat to a subsonic flow, finally its Mach number will become 1 at point A. Similarly, if we add heat to a supersonic flow, its Mach number will decrease and eventually it will reach at point A, meaning Mach number 1. So we can say that Mach number M approaches 1 in both the cases of subsonic flow and supersonic flow during heating. And the fourth observation we can make that from the energy equation we can write Q equals Cp times T02 minus T01. From this equation we can conclude that if we add heat to the flow, meaning Q is positive, we can see that stagnation temperature T0 will increase during heating, and during cooling T0 stagnation temperature will decrease during cooling, and we can see that maximum stagnation temperature will exist at point A. Maximum stagnation temperature. Similarly, static temperature T will also increase. But for this small range of Mach number 1 by root gamma to Mach number 1, you can see from the diagram that static temperature is decreasing. Static temperature T is decreasing, and it may seem odd that the temperature drops as heat is transferred to the fluid, but this cooling effect in this region is due to large increase in fluid velocity. Consider this equation: T0 equals T plus V square by 2 Cp. In heat addition, T0 will increase, and similarly velocity and temperature will also increase. But for this small range of Mach number 1 by root gamma to 1, what happens that the increase in velocity is very large and the temperature decreases. Now what will be the effect of heat addition to static pressure P? So from the momentum equation we know that P plus rho u square is equal to constant, and we also know continuity equation, which is rho into u equals constant. Now we can write momentum equation as P plus rho u into u equals constant, and from the continuity equation rho into u is constant, we can write it as K. So our momentum equation will become P plus K times u equals constant. P plus Ku equals constant. Suppose that our initial flow is subsonic and we are adding heat to the flow, what will happen? we know that if we add heat to the subsonic flow, its velocity will increase because Mach number increases. So what will be the effect on static pressure? Static pressure will decrease. Static pressure will decrease if we add heat to the subsonic flow. But if our flow is supersonic initially and we are adding heat to the flow, we know that its Mach number decreases and hence its velocity is decreasing. Velocity is decreasing, and hence from this equation we can conclude that its pressure will increase. Its static pressure will increase. So if we add heat to the subsonic flow, static pressure decreases, and if we add heat to the supersonic flow, its static pressure will decrease. Now what will be the effect on density? So from continuity equation, rho u is equal to constant. We know that if we add heat to the subsonic flow, its velocity increases, and from this equation, density is inversely proportional to velocity, and hence density will decrease if we add heat to the subsonic flow. Now consider another case in which we are adding heat to the supersonic flow. What will happen? Its Mach number is decreasing and hence its velocity. So from this equation, if velocity decreases, its density should increase. So look at again on the graph. If we add heat to the subsonic flow, its temperature and Mach number both increases, but for this small range of Mach number 1 by root gamma to 1, static temperature decreases, and at this point at which Mach number is 1 by root gamma, temperature T is maximum, and we will prove that maximum temperature exists at Mach number m equals 1 by root gamma in subsequent lectures. Next we will consider the effect of heat addition to stagnation pressure P naught. Now when we add heat to the fluid, its entropy S increases, and we know that whenever entropy increases, its total pressure or stagnation pressure decreases. So whether the flow is subsonic or supersonic, if we add heat, the total pressure or stagnation pressure will decrease. In another way, we can say stagnation pressure always decreases during heating. And the opposite is true for cooling. For cooling, stagnation pressure will increase.